Okay, so this lecture we will start with the definition of complex numbers. I think most of you already know that, but we would like to recall some basic properties. Okay, so addition and multiplication of complex numbers. We will use this mass BBC to denote, recall that in LaTeX, use mass BBC to type in this symbol. So this is defined to be A plus IB, where AB are real numbers. I is square root -1. So in particular, I squared is -1. So as a set of points, C is the same as R2 is a two-dimensional vector, so xy. So A plus IB is the same as AB as a vector. And we call A the real part. And denoted by RE. This is A. And the imaginary part, A plus IB, this is denoted by IM, A plus IB, which is defined to be B. So actually this is X coordinates, this is Y coordinate. Of course, R2 has some Euclidean structure, that is addition. So A plus IB plus C plus ID, you can define to be A plus C plus IB plus D. This is the same as addition for vectors. Okay, and then the difference between C and R2 is that we have multiplication on C. This is different because on R2 we only have scalar product. That is, you can times A and B by number lambda at the same time. But here on C we have different structure. Actually in mathematics, in advanced mathematics, the thing we're interested in not only the set, but the relations, the structures on the set. The structure is the most interesting and important part, not only the isolated points in the set. Okay, so the definition is the following. A plus IB is an arbitrary complex number times C plus ID. This is defined to be A times C plus IB times, we use the distribution law, A times ID plus I squared BD. And you plug in I squared is -1. Then we have AC minus BD plus I BC plus AD. Okay, note that by definition, this is a point in the complex plane. Therefore, this operation is well defined on C. Okay, next we define the absolute value. And so this is a squared plus b squared square root. If you look at the picture, then this is the length of the vector AB. So this is the same as the R2 structure, Euclidean structure, but in different notation. And now we have another one, which is special for the complex plane, complex conjugate. So A plus IB, you take the complex conjugate, you define to be A minus IB. If you look at the picture, what does that mean? That means you reflect A plus AB along the x-axis. Okay, then immediately you have the following property. The norm of A plus IB is a square root A plus IB times A plus IB bar. You can just verify it. Okay, now let's look at some proposition. So first, this is the same as a Euclidean one, Euclidean space R2. If a complex number is 0, if and only if the norm is 0 and the real part equals imaginary part equals 0. And secondly, the real part of a complex number is always less than the norm or the absolute value. The same holds for the imaginary part of a complex number. And thirdly, the norm of a complex number is the norm of its conjugate. Okay, and 4, the real part can be computed in the following way. The complex number plus its conjugate divided by 2. Or if you like, we can write in this way. Similarly, the imaginary part of a complex number is the number itself minus its conjugate divided by 2i. Or you can write in this notation. Okay, so exercise what is the real part of this quotient? We will come across this type of quotients a lot later. So let's compute it. The way to solve it is we times both up and down by the conjugate of the denominator. Okay, then the denominator you will have a complex number, this c squared plus d squared. In the numerator you have a plus ib times c minus id. This is real part ac plus bd plus I bc minus ad divided by c squared plus d squared. Okay, then it's clear the real part is ac plus bd divided by c squared plus d squared. And also you have the following property. Suppose so the product and the addition is commutable with a complex conjugate. You have this one and z1 times z2 take complex conjugate. This is same as product of complex conjugates. And similar to the Euclidean space R2, we have the triangle inequality. The norm or summation of two complex numbers is less than or equal to the summation of norms of complex numbers. So we give a short proof here. To prove this inequality, it suffices to show that the following equality is true. This is the square of the original equality. And then the left-hand side equals z1 plus z2 times conjugate of z1 plus t2. The right-hand side, you just expand it in the usual way. Okay, and then left-hand side, you compute it, you find this is z1 squared plus z2 squared plus z2 z1 norm plus z1 z2 norm less than plus 2 z1 z2. Okay, and then note that this is less than or equal to this. Therefore, the theorem holds. Next, we introduce another convenient form for complex numbers. Just like in R2, we have rectangular coordinates and also polar coordinates. When we do multiplication, sometimes the polar coordinates is more convenient. So suppose you have complex number z, then you can write it as r times exponential I theta. So here r theta are real numbers. it's clear the R is unique. Theta is not. It's only unique up to 2k pi. That because exponential I 2k pi is 1. Okay, suppose you have another complex number, omega. Omega is R exponential I phi, or cosine phi plus I sine phi. Then you can verify that. So recall, I should make a remark. I haven't tell you how to define exponential I theta, right? Later on, we will give you the definition by power series. Then it's similar to exponential theta. Okay, when theta is a exponential x, when x is a real number. For x is a real number, we already know how to define it. But for this one, we only take it formally at this moment. Then, if you want to, so I claim. So claim z times omega. If you look at this part, what can you guess? You can guess the answer will be r times smaller r times exponential I theta plus phi. This is very natural, but unfortunately we need to prove it because we don't know. We need to prove it because at this moment we don't know exponential I theta times exponential I phi equals exponential r theta plus phi. Although this is true when the power is a real number. Okay, so to prove the claim, we need to go step by step, show that the following equality holds. Sine theta plus phi. Okay, this can be done by trigonometric formulas, so I will not repeat that. And after we introduce polar coordinates for complex numbers, then immediately we have the following formula for powers and roots. Suppose z is r times exponential I theta, then z to nth power is r to nth power exponential I n theta. And secondly, nth root of z is given by a1, a0 all the way to ak an minus 1. So where ak is, you take nth root of the magnitude r, and then for the angle you need to divide it by n. But the problem is you can add 2k pi to it. Okay, so first one is obvious. For the second one, we can check that ak to n's power is r times cosine theta plus 2k pi plus I sine theta plus 2k pi. This is r cosine theta plus I sine theta, which is z, for all k from 0 to n minus 1. So you have n roots, and also by the fundamental theorem of algebra. Well, we will prove this theorem later, after we know the maximal modulus theorem. We have at most n roots for a polynomial equation of degree n. So this is done. Okay, next we are going to recall some basic properties from mathematical analysis about differentiability. We will use this a lot later on to verify some basic definitions. So although we know it from mathematical analysis 521, I would like to recall it again. So suppose f is a function from R to R, and f is differentiable at point x equals a if there exists a real number L, such that for all epsilon greater than 0, there exists delta greater than 0, such that fx minus fa divided by x minus a minus L less than epsilon for all 0 minus for all x minus a between 0 and epsilon. The absolute value of x minus a between 0 and epsilon. If you are not familiar with this definition, please refer to Rudin's book or any other equivalent mathematical analysis book. And so a corollary is, if f is differentiable at x equals a, L is unique, and therefore we define, or we make the following notation: f prime a equals L. The derivative of f at a is L. Okay, then this is a 1D case, and for 2D, you can generalize it in a similar way, but a little bit more complicated. Probably you learned that from 522. So, but anyhow, let's define it. So we call a function f from R2 to R differentiable at point xy equals ab if there are real numbers a, b, c in R, such that when xy goes to ab, the following quantity goes to 0. Okay, note that what it is. This is a linear function. So that means this linear function gives a very good approximation of original function at the point AB. So that's a definition for differentiable multivariable function. And actually, so to compute AB, just recall, to compute AB, capital A, capital B, capital C, we can take special route to approach the fixed point AB. So suppose this is AB. If we take your point x, y, go to AB vertically, then actually we can compute B. And if we take the point x, y go to AB horizontally, we can compute the constant A. And so more precisely, if f is differentiable at AB, so capital A is a partial derivative of f with respect to x at point AB, and B is partial f partial y for fixed x at point B, where y is B and C just a value of f at AB. Okay, now let's consider a little bit more complicated case. Suppose f is a function from C to C. Then actually what do you have? You have a multivariable function, vector valued function. Okay, and so to talk about differentiability, we usually specify all the real numbers, because in 521 and 522 we never talk about the complex version of differentiability. This is not so precise. You have a lot of different versions of complex differentiability, but for the real variables and the real vector valued functions, the definition is unique. So first, we write everything in real numbers. For the variables, you have x plus iy. For the vector valued function f, you write it as real part plus uxy plus imagined part ivxy, where uv just r2 to r. So this is the case we just discussed above. Okay, and so differentiable f is differentiable. So actually here I need to use a comma because later on we will introduce a stronger differentiability. But here, this differentiability, we just says is differentiable as a complex value function. More precisely, at point z equals a plus ib is defined to be equivalent to the following conditions. So uxy is differentiable at a plus ib. V is differentiable at z equals a plus ib. Nothing special, just two components, u and v, are both differentiable as multivariable as functions on multivariables x and y. And I should make a remark that so everything so far is trivial from the point of view of complex, from point of view of complex analysis, and will not be the main topic in this course. By this, we mean that we were not so interested in the differentiability of some special functions. For example, how smooth it is, how many derivatives you can take, and is it integrable or whatever. This is not the main topics of this course. Actually, later on we will show that the main topic we are interested in is always smooth. You can take as many as derivatives you want. You can do whatever algebraic manipulation you want, just as good as polynomials or rational functions. Yeah, so we need to find some underlying better properties of the subject we are interested in, instead of just the differentiability. So that's another point I want to emphasize at this point, that in science, we only study special phenomena. For example, our universe itself is very special. So far, no other human beings be found outside Earth. Okay, and narrow down to complex analysis, we will study differentiable complex function with an extra symmetry. So there are many different interpretation of the actual symmetry. I will introduce some of them. So first way is that we require the following holds. At first sight, this seems strange why we have such a weird condition, but at least it tells you that for the objects we are interested in, we want to. So basically, you have two partial derivatives of f, x derivative and y derivative, but in the objects we are interested in, we want to know the other derivative based on the one derivative. As soon as we know x derivative, we expect to get information on the y derivative. Then there must be some constraint on that. Not all the differentiable functions have this property. And later on, we will show that why we have this type of conditions instead of y naught plus 2, equals 2 partial f partial iy or whatever. Because to determine one derivative, you have many ways. You can have linear dependence, you can have some quadratic equations or whatever, but here we choose this form. The reason is not clear at this point, but we will specify it a little bit later. But this already gives you some interesting phenomena. So if you rewrite the condition, you will have the following. If you still remember what we learned in 234, that this is called partial differential equation. So the subject we are interested in is a complex function satisfy a partial differential equation of first order because you only have one derivative. The derivatives are only of order 1. You take first order derivative, and we call this Cauchy Riemann operator. Just recall in 234, we already know the wave operator, that is partial t square minus partial x square minus partial y square minus partial z square f equals 0, and also heat operator partial t minus partial x partial y partial z square f. So this is wave, this is heat, and also Laplacian. In 2D, you will have, those are 3D. In 2D, you can have similar thing. In particular, the Laplacian take the following form. And just a little bit later, we will show that this is closely related to the Laplacian operator, Cauchy-Riemann operator. But here we already have some generalization because in Math 234, you only consider the operators with real coefficient. But here you have complex coefficient I, and the function is a vector valued function. Okay, so this is a little bit more involved thing. Okay, now let's simplify this operator in components. Suppose f is u plus iy. So in complex world, everything not just components. Different components will mix together. This is a high generalization of the Euclidean space structure, and it's very special. It only works in R2. In R4, it will be different. And actually, the Dirac equation is another generalization of the complex valued. In that case, the numbers, the products, are not communicate, but then this gives a interpretation or make the Schrödinger equation relativistic. So all I want to emphasize is, starting from now, you should be very careful and be familiar to the structures on the sets instead of just vector values in or whatever. The complex world is not that complicated, but it's very ample. Everything mixed together and make life very interesting. Okay, now let's simplify this. You just use distribution law minus plus I partial y u plus partial x v equals 0. Of course, since x, y, u, v are real valued, therefore this is equivalent to two equations. Or I would like to write in this way. Vy, ux is vy, uy is negative vx. So this is also called Cauchy Riemann equation. Just the Cauchy Riemann operator acting on functions in components. Okay, so now let's talk about another definition, and which explains why we have the Cauchy Riemann operator instead of some other first order differential operators. So here we view z as a whole thing. That is, you view it as a single variable, and f z to z, c to c is a function of z. Okay, and if we want to generalize, a naive way to do that is formulated as the following way. We call fz complex differentiable or more standard notation is holomorphic if there exists L, but now it's a complex number such that here differential at z equals a plus ib. Yeah, you should fix the point. If there exists L such that limit z goes to a plus ib, fz minus fa plus ib divided by z minus a plus ib minus L equals 0. Actually, if you view, you can go back to the first example we discussed here. It's very similar to this version of differentiability, or a single or a scalar function depending on a real variable. Okay, so here is our generalization, and then of course we need to, let's write down the condition start in real variables. So let's see what we really have. So this is just a guess. We want to have something like this as a generalization. Okay, now we first write L to be capital A plus I capital B, and F to be U plus I V. Then what do we have? Also U X Y plus I V X Y. So Z is X plus I Y. We put everything in real variables. And then let's compute the limit of this quotient. So here, then we have, this is limit Z goes to A plus IB. Oh, sorry. We put into real variables. X, Y goes to AB. Then UXY plus IVXY minus UAB minus IVAB minus A plus IB times X plus IY minus A minus IB divided by X plus IY minus A plus IB. Okay. Okay, then you can split this into real part and the imaginary part, and then you will, I omit this, I leave it to you. Y. Then you will have A is partial U partial X. Recall that we assume f is differentiable as a vector valued function depending on variables x and y. A is partial U partial X, and also partial V partial Y. B is partial U partial minus partial U partial Y partial V partial X. Okay, in particular, what do you have? So from this one, let's see. So for such L exists, you need to have this properties hold. So what is this? If you look back to this one, just a Cauchy-Riemann equation. So this approach is more natural. It tells you why we expect that, because we want to have some analog for real stuff. Okay. And but the computation a little bit messy. But for the first approach, although it doesn't tell you the motivation, but it's easy to remember and manipulate. So next time we will discuss more of this, and in particular, next time we will show that. So such L can be written down as partial y f. Okay, we will stop here and continue next time.